Hello everybody, welcome for the second tutorial here for Simulink. And today I'm going to show you how to simulate an actual model, so to have a better understanding. Let's share. Here we see a pendulum, which is the easiest model I could think of. And let's study the dynamics. Let's say that the pendulum has a massless bar here of length L with a mass at the bottom. And this mass, of course, is affected to gravity with the force I've divided into the perpendicular and the parallel component. And then since the mass is moving, we have inertia. So really easy. The acceleration for the inertial, as everybody knows, we can connect angular acceleration to actual directional acceleration in this way, which is proportional to the length L. And we can get the equation of motion just by applying Newton, and such that the summation of all the forces that need to be 0. So here we can see the mg sine theta has to be equal to the inertial for the perpendicular component. After substituting the acceleration, we get to the following form, which reduces to this ODE. This is the one that we're going to simulate here in Simulink. G, of course, is the gravity, which is 9.81, and I've selected 3 right now as length, but you can select whatever you wanna, and doesn't change much. But this is basically the ODE we're gonna solve with Simulink. So let's start that. Let's Simulink, a new model. Here we go. Let's move myself up. Well, let's start with a constant, therefore. Value 3, I said. This is the length. I'm going to try to simulate this in 2 ways. First of all, I'm going to simulate using only Simulink blocks. And after, I'm going to try to recreate the results. First of all, to match it. And second of all, to give you more information using MATLAB a little bit. And so basically by implementing MATLAB functions inside Simulink, which is something that everybody loves to do. You're going to use it a lot, so it's better for you to know how to do it right away. The first thing we want to is the integrator. Let's say this is the integrator from the acceleration to the velocity. And let's say that we are moving the mass and we are just like letting it go. So not pushing, not anything, we just let it go. So we start with 0 velocity, and I pick 0. I want another integrator. Then this is going to be from the velocity to the position. And let's say that like I move my mass up to phi 30. Phi over 3, I'm sorry. So I'm going to put it here and connect it. In order to have a little bit of understanding and write it down, this is going to be theta dot dot. Let's leave another annotation. It's going to be theta. It's going to be theta dot here. Now, what I have to do, I have to create basically this equation here, which is theta dot dot is equal to G over L sine of theta. Of minus G over R sine of theta. So let's create a divide block in this case. And as a number of inputs, I want multiplication, I want a division, and another multiplication. Here we go. Let's make it bigger so it's easier for you to see, since I have no idea how Zoom is working for recording. What I have first, I have another constant, which value 9.81, which is gravity. Gravity. And I'm gonna be my first multiplication. Then I'm dividing here. It's like theta dot dot equal minus G over L. So it's gonna be our length. Then theta needs to be we have to do the sine of theta. So just writing down sine, here a sine. Now, some useful commands, you do Control I, it switches the direction. While if you want to do Control R, it just rotates here. Good to know. You're gonna use it a lot. So here we have sine of theta. However, we have not finished because it's minus. So I can just put a gain -1. Here. And this should be done. Now my system is finished. If I make it run, however, it compiles, it's done, but I have no idea on how it's behaving. In order to do that, we need a scope. Let's say I want two ports because I want to know both the position here and the velocity together. A bit bigger. So make it run again. What are we seeing here? In yellow, we have the position, which is indeed, it starts at phi/3, which is around 1 indeed, and is a sinusoidal behavior. The velocity that starts at 0 is maximum where the position is 0, and vice versa. Our position is maximum when the velocity is 0, which means like indeed maximum position, maximum deviation, like maximum theta, is maximum when the velocity is changing sign, and like when the ball is at the bottom is the fastest, which is where position is indeed 0. So it looks like he's behaving good. Let's try to do it again now with using MATLAB functions. So the first integrator with initial condition 0. I'm not gonna write again theta dot integrator, initial condition phi/3. Connect this. And now I'm gonna write MATLAB function here. Put it here. Let's open the function and you will go back to the normal MATLAB function. So now, see a function. I can call it whatever I wanna. Let's say I call it dynamics. And let's try to be consistent. Theta, let's say, here you decide all the inputs you want in your function, and just want theta and the length of the pendulum. And let's say that the output is theta dot. So let's define G as 9.81. And then I'm basically done. Let's write theta dot is equal of what? Minus is G over the length times the sine. Hopefully I'm not going too fast. You can pause the video. And this should be all. Save it. In the model actually. Pendulum. Okay. Yes. Let's go back to our model. I'll add another model. As you can see, now that we added another input in the MATLAB function, the block changed and is now asking for 2 arrows. And it is telling us the name. See, this is theta, this is in the length, this is theta dot dot. So the order is the one you have in the function. So let's just do this. Let's connect theta back. Let's put it closer, just because. Well, again, a scope with 2 cores. Let's do this. Let's do this. Let's run it. One. Let's check it's the same as the other one. And they indeed are the same, which is good. And I think it's done for this second video. What can I do? So see, now we have done, like, we simulated the dynamics of a system. Let's say that I want to keep order of it, so I can just like say I want to still keep an output on the performance, so I can subsystem and say like call this subsystem has dynamics with MATLAB. And when I go inside, here we go. We have in, which I don't like, since I want to keep track of my inputs and outputs. So I'm going to call it length. And as output, I'm going to just call this theta, or position, as I say, right here. And say velocity. See, now we're working in the first subsystem. What can I do now? I go back. So this is the same here. Let's say dynamics with Simulink. Let's go inside. So this is the length. This is the gravity. This is my theta. So I said velocity, and I call it position. Back. You know, you will usually decode the code twice. The first time to make it work. The second time it's after you make it pretty and you broke it. So let's look for it. It still looks like it's working good. So I didn't break it. And that's good. Yes, save it. And therefore, we have simulated a system, a pendulum. Next time we're going to try to control it. Therefore, I think it's a good time to stop the second tutorial. Goodbye.